All right, so this last lecture chunk will wrap up the first lecture series on water. And we're going to use this to tie up loose ends and refortify some concepts instead of introducing anything really new. We're going to go back to talking about pKa's because they're important and obviously they're a little bit dense and complicated. And we're going to discuss them in a completely different way to fortify what pKa's are, what they tell us, how they work. So no new material, just the same material taught in a different way from a different perspective. So we are once again returning to acids, bases, pHs, and buffers will be the lens or the context that we look at pK through today. So we can define a buffer as anything that resists change. Even in normal speech, this is what we mean by a buffer. If a boss hires an assistant to be a buffer between her and the people who work for her, that means that she wants that person, that buffer, to help her resist change from those underlings. So a buffer is anything that resists change. In this context, a buffer is something that resists change in pH, because that's what we're discussing. So biochemical buffers typically stop pH changes from occurring. The way that you make a buffer is pretty simple. It's just a solution of a weak acid and its conjugate base. That's all you need to make a buffer. Have a weak acid and it's somewhat dissociated, so some of that acid has gone up, given its proton, and become a conjugate base. Weak acids have strong conjugate bases. That shouldn't surprise us. That makes some common sense. If we think of these beautiful doggies, if we think of these dogs as molecules in solution, and this poor stuffed bunny as the proton in between, this is a weak acid, this dog here. This is a dog that does not want to give up its proton, right? You can see, fighting to keep that proton. And this is a base in the solution, also fighting over that same proton. This is a weak acid. Strong acids are defined as acids that readily give up protons. Acids that do not readily give up proteins, just as this dog is not readily giving up its bunny, is a weak acid with a low Ka, a high pKa. Now, let's say the dog on the left wins, and it gets that stuffed bunny away. It forces this acid to donate its proton, and now this dog would be bunnyless. This dog would be the conjugate base. It's lost its proton. If you were to intervene and take that bunny away, how readily do you think this dog would take it again? Chances are this dog's going to go nuts to get that bunny back. It wanted it all along. So any molecule that readily and quickly accepts a proton is a strong base. So a weak acid gives you a strong conjugate base. In other words, if it took so much effort to get that proton away from me, because I never wanted to give it up in the first place, I was a weak acid, I'm going to gobble that proton back up again, speedy quick, if I have the chance to, making me a strong base. Likewise, strong acids make weak conjugate bases. A strong acid is, hey, you want this proton? Take it, it's yours. You want it? Go ahead. I'm a strong acid. You can have it. And then when you try to give it back to me as the conjugate base, you ask me, do you want that proton? No, I told you you could have it. I don't want it. That makes me a weak conjugate base. So things that readily give up protons, don't want them back. Strong acids make weak bases. Things that desperately don't want to give up protons are weak acids, and they'll take those protons back again very quickly, making them strong conjugate bases. So that's what's all said here in the text of the slide. So with that in mind, let's go back to buffers. When we have a buffer solution, we have a weak acid that is partially dissociated. So some of those acid molecules are still weak acids. They're still protonated. They still have protons. But some of those weak acids have dissociated. So now they are strong conjugate base. And that strong conjugate base is hungry to accept free protons, any free protons it can. That's our buffering solution. Now imagine if we add strong acid to that buffered solution, the minute that acid hits that solution, it's going to give up its protons. Those protons are readily given up by the strong acid, but in that solution is strong conjugate base. Strong conjugate base from our buffering solution, which gobble up those free protons right away. And without those protons remaining free, we don't see a change in pH. Excuse me. The solution is buffered. Compare this to water, where you add the same amount of strong acid when there's no buffering. That strong acid, as soon as it hits the water, gives up its free protons. Those free protons have nowhere to go, and the pH drops off precipitously. because those free protons contribute to a more acidic pH. These buffers also work for bases, so if you add a strong base to your buffered solution, that strong base is going to rip proton off of your weak acid, your buffering acid, and neutralize itself that way. As long as we have a solution that contains weak acid to neutralize strong base, and strong conjugate base to neutralize any added free protons, we will have a buffered solution. The pH will be kept stable and constant, and that's what we want. That's why we made the buffer in the first place. So this isn't going to be a clickable link, unfortunately, but if you were to type this link into your browser, if you open another tab, you'll be brought to a virtual buffering activity where you can play with these. I'll go ahead and show you that very quickly here. Give this all a second to load.
A buffer is an aqueous solution.
So there's audio, as you just heard, that launched that you can listen. It'll talk you through this. What we have here is a buffered solution. We have the weak acid, and it's the proton here, this little gray ball, a weak acetic acid, vinegar acid that's floating around, and it has been partially dissociated. It's 50% dissociated. And so we have the strong conjugate base acetate. Now let's add strong acid and see what happens. pH should go down if you add strong acid because you're adding free proton. So we add strong acid, and look what happened. That strong acid has linked up immediately with our strong conjugate base, and those protons are not free, and only free protons contribute to pH. And so the pH has remained steady because we have that strong conjugate base in there to absorb those protons. We can add strong base as well, like hydroxide ion, and we see that strong base is stealing protons from the non-dissociated acetic acid, neutralizing itself from hydroxide ion to water. And so again, pH is not changing because that strong base does not remain base for long. So go ahead and play with that, get a sense for what we're trying to show, and see if that helps you understand those concepts. So all this raises an important point. When that animation ended, when we added the strong acid and we left it there were only 2 molecules of conjugate base left in that solution. So that means we can run out of conjugate base. If we were to add 4 or 6 or 8 more molecules of that strong acid, we would eventually overcome or swamp out the available conjugate base, and there would be no more strong conjugate base available to absorb protons. Those additional protons would remain free, and the pH would begin to change. That's a true property of buffers. That happens. That's called breaking the buffer, and all buffers can be broken in this way. So the idea is that as you add acid, that acid dissociates into free proton, and the free proton is instantly gobbled up by the strong conjugate base that's buffering the solution. But as you continue to add strong acid, and you continue to add protons, you can think of the conjugate base in that buffer as a sponge, and eventually the sponge will become saturated with free proton. If you still add more free proton after that, that sponge is so saturated that it simply cannot absorb any more water, and those added free protons will contribute to a change in pH. The pH change occurs rapidly when the buffer is broken. All buffers can be broken. That occurs when all available conjugate base present in the buffer has been converted back to weak acid because of its absorbing of a free proton. There's no more available conjugate acid in the solution to absorb further protons, and so the protons that you add contribute to a change in pH. Again, as I say here, since there's no base left to soak up those protons, any more protons you add after causes the pH to change dramatically, causes the pH to go down just as it would in water. So when using this in a practical setting, you always want to pick a buffer that has a pKa near the pH you're shooting for, the pH you want to keep stable at. The reason is because if you buffer your solution at that pH, then your pH is nearly your pKa, which means you'll have 50% weak acid available to neutralize any strong base that's added, and you'll have 50% conjugate base available to neutralize any acid that's added. If you have a pH of a solution near the pKa of your buffer molecule, you'll have equal amounts of weak acid and strong base to absorb the addition of any additional acid or base that you might have. Buffer is usually effective up to 1 pH unit on either side of its pKa, and so most buffers have a 2 pH unit range. Here are some commonly used buffers in biochemical settings. Pipes is used very often because its pKa is 6.8, very, very close to 7. Tris you've probably used already, even if you don't realize it. Tris is very commonly used, and it's usually pH to 8. The pKa of Tris is 8.3. Phosphate buffer is here. We talked about it being a polyprotic acid, which is why we have 3 different pKa's. And maybe some of you have used tricine. It's a little bit of a harsh molecule, not the safest thing to be around, but it has a pKa of 8.15, and it buffers very nicely at a pH of 8. In living cells, we maintain a phosphate buffer naturally that keeps us at around a pH of 7, with that second proton being the one that's added or donated to keep those solutions buffered. And in the blood, we have carbonic acid, a carbonic buffer, which is based on carbon dioxide itself. So to summarize this material, buffers are solutions of a weak acid, and it is therefore strong conjugate base. Because of the presence of weak acid and strong conjugate base, buffers can absorb added free proton through the conjugate base, buffering on that end, or can neutralize strong base that's added by donating a weak proton and keep it buffered on that end as well. Either way, we have resistance to changes in pH. That's the end of the Lecture 1 material. Even though each lecture is not so long here, A, B, C, and D, together these make up more material than most of the lectures will wind up being. So I appreciate you watching and coming on this firm footing of water and all of the many things that it does. We'll be moving on to protein structure in our next lecture series coming up next in Lecture 2. Thanks for watching.